So our last speaker, but not the least, is Vladimir Šviković, another PhD student from our research center. You can use this one. Vladimir is working on problems of control in power electronics, especially in the field where it's necessary to produce really fast dynamic response of your converter. And we are going to hear his presentation about this topic. So Vladimir, when you feel free.
Thank you, Mr. Chairman. Good morning, ladies and gentlemen. Thank you for coming. Today I'm going to present you the work we have done regarding the optimization and analysis of fully integrated power sock buck converter for automotive application. During the last few decades, electronic content of vehicles have grown drastically, and with the emerging electric car just out of reach, a lot of effort has been placed in development and optimization of electronic systems, especially power supply chain. So, in the classical conventional switch-mode power supplies system, most, if not all, of the components of the system are discrete, which is increasing the cost of the product and it is increasing the weight. And the goal, of course, is to have not to influence that much on the weight of the whole system in order to improve the efficiency and the lifetime of the battery. So the tendency is to minimize the whole system, and in power system on chip, the idea is to fully integrate the whole product together with the load in the single chip, if possibly in the same compatible technology from which the load has been made. If we analyze what is the dependence of the footprint area of the whole system on the switching frequency, we can start from around 50 square millimeters for this range of power, switching at 1 megahertz, and as we increase the switching frequency, we can finally achieve a full integration of the whole system, allowing smaller cost and, as I said, smaller weight. So, in order to tackle this problem, under the funding of European Union, a power type consortium has been made, composed of Tyndall from Ireland, Infineon from Germany and Austria, Bosch from Germany, IPDIA France, Ampere Laboratories from France, and UPM, in order to design this system. The idea is, as I said, to have full integration with a compatible current technology of 40 nanometers and to obtain the system with relatively high efficiency, good dynamic performances, and small footprint. The first question that occurs here, what is the optimal architecture? And in this presentation, we're going to focus on single stage solution. So in the state of the art, there are a lot of solutions already proposed. On the x-axis, we can see the technology which is used for integration. On the y, we can see what is the input voltage that can be supported by this device. The color determines the efficiency of the system at the typical power, and the size of the circle, or the x, gives us more or less the idea what is the footprint of the device. So, for instance, this point here, it is using 500 nanometer silicon technology. It has the input voltage of 4.5 volts, 80% efficiency, and around 10 square millimeters footprint. On the other side, we have 45 nanometer solution with 1.8 volts maximal voltage and 70% efficiency. We are tackling in two different branches, 40 nanometers technology, which is adapted to support 5 volts and the input voltage, or 3.3 input voltage. So, in order to truly optimize this design, a designer has, the idea is to have an integrated system to satisfy specification while converting the input energy to the output energy. One of the most critical parts of the specification are the output power, the area budget in which we can allocate the passives and the semiconductor components, the static output voltage ripple, the output deviation, input voltage ripple, and of course we want to obtain a system that has high efficiency in a wide range of the output power load. So, as I said, there are various options that need to be taken into account. So the first one is what is the optimal topology to be used, which technology for the inductor, capacitors, and semiconductor can we integrate, which type of control should we use to tackle the dynamic part of the specification, and which modes of operation we need, we can operate under in order to improve the efficiency. So having in mind that the designer needs to optimize all this from the beginning, it's advisable to use computer-aided design tools, such as this one. Here, the user can define the parameters regarding the capacitor technology, the inductor, semiconductor. It can define what is the total available area for the passives, define the static specification, dynamic specification, define the regulation, topology, modes of operation. It can preload already optimized design, which is saved, and perform the analysis. And of course, the key point, it can optimize the whole system. When we say optimize, the user can select which component of the system he wants to optimize. And at the end of the optimization, he is obtaining all the crucial data regarding the geometries and the values of all components of this system. So in order to build up the tool, first step we needed is to develop design tools such as models based on technology and topology, and to define what is the valid design space based on topology and control for this specification. Together with the modes of operation, we can evaluate what are the losses of the system, and finally we can optimize to obtain the final design. In this presentation, I'm going to show you only the part of the work we have done, and we're going to focus on what we call what-if analysis, which is actually a technology impact analysis on the system. The optimization for each point of the operating frequency has been performed using the power swipe specification. And we analyzed first what is the influence of the actual inductor technology, while assuming that the rest of the system is ideal. The second analysis that we performed is the opposite one. What is the impact of the semiconductors on the system while the rest of the system is ideal? Then we added to this solution, to this scenario, only conduction losses in the semiconductor to see what will happen. And finally, we analyzed the full system with both actual semiconductor technology and inductor technology. So in the case when we have actual inductor technology, on the left graph we can see what is the efficiency, and on the right we can see what is the area distribution of the system. Interesting part here, we can notice how the efficiency is increasing as the frequency is increasing. This is due to the fact that we can use smaller and smaller inductance to satisfy the specification. Thus, we are able to integrate on the available inductor space better and better inductor, thus reducing overall losses. On the other hand, on the low switching frequencies, since we have high current ripple, we need bigger capacitors to satisfy the same specifications. So this big capacitor area is limiting available area for the inductor, and we are worsening our design, putting more losses in the device. Then we performed the same analysis for the case when we have available area of 8 square millimeters and when we have the available area of 18 square millimeters. First, we can see that we are not gaining that much in efficiency even if we have more available space. In these two graphs, you can see what is the area of the inductor for the two cases and what are the values of the inductances for all three cases. First, on the higher switching frequency, since we have more available area than what is the optimal one to design the inductor, the design saturates and we are not achieving much improvement of the system. On the other side, for the low switching frequency, as I said, the available area is defined by the capacitor area, so we can see that For the case of 13, we have only 8 square millimeters for the capacitor, so we need to put more inductance in the inductor to satisfy the same specification. While in the other case, we have more area for the capacitor, so we can reduce the inductance to improve the efficiency of the system. And finally, for the scenario of 8 square millimeters, there is no valid solution at 2 megahertz, since there is no space for the inductor in this scenario. Then let's switch to real semiconductor technology. On the left graph, we can see what is the efficiency, and on the right, we can see what is the breakdown of the losses depending how they are depending on the frequency. And as expected, the efficiency is dropping as the frequency is increasing due to the fact that the switching losses are predominant. Since for each point, the design has been optimized in nearly all the range, the ratio between the switching losses and the conduction losses are around 65% to 35%. So at this moment we saw that the tendency of the inductor technology is to push the optimal design at the high frequencies, while the semiconductor technology has the opposite trend. So we're going to have some solutions somewhere in between, and for the actual semiconductor and actual inductor technology, we obtained the maximum at 12 megahertz. Let's go back to the semiconductors. If we are able to somehow improve the semiconductor technology, what will happen with the system? We improved it by factor 2, which means we reduced the on resistance by 2, and we reduced the switching losses by factor 2, and we obtained higher efficiency. Since the switching losses are predominant, we are gaining more on the higher switching frequencies. Again, we obtained 2% on our optimal switching frequency, so of course there is an urge to improve the technologies that we are using. And finally, if we compare with the tendency of the actual inductor, we can see that the optimal point is around where the losses are balanced. And the interesting part is that if we improve the semiconductor technology, the optimal point will shift to the higher switching frequencies, allowing us to easily integrate the inductor. Then we added, in this system, we added conduction losses in the inductor. And here we can see the efficiency of the initial system only with semiconductors, and efficiency dropped when we added the losses. At the 12 megahertz, we lost 5 points of efficiency. Regarding the losses breakdown, as expected, the inductor losses are reducing as we are increasing the switching frequency, while the semiconductor losses are having opposite trend, giving us a total losses which are having minimum at 4 megahertz. And final design, we have the same tendencies in both inductor and semiconductor losses, giving us once again total losses of the system and the overall efficiency. The maximum is at 12 megahertz, but what is interesting here is that we have a wide range of operating switching frequency where the losses are not changed drastically. So we can perform a trade-off between the temperature stress on the semiconductors and between the integration of the inductor to facilitate the design of the system, implementation of the system. So at the end, we saw what is the impact of the current inductor technology that we are using, and that is moving the optimal design to higher switching frequencies. Then we saw what is the impact of the semiconductors, and that the optimal design is shifted to the lower switching frequencies. We added the losses, conduction losses in the system, and the optimal point shifted from the low switching frequencies to 4. And finally, in the actual semiconductor technology and actual inductor technology, the optimal point shifted further to the higher frequencies at 12 megahertz. At the end, in order to optimize and integrate this system, it is recommendable to use computer-aided design tools. And we saw what is the impact of the technologies. So if we are able to improve one of the technology, we would know how it will affect the system. And at the end, this is all part of the Power Site project, as I said at the beginning, which at the moment we are now closing up the first initial design of the system, and we are entering the process of fabrication. Thank you all for your attention. So if you have any questions.
So we still have a few minutes for questions and answers, so if there is any question, please. Actually, I have one question. I mean, can you just show the efficiency graphs once again? The last slide, I believe, or previous one.
This one?
Yes, that one. I mean, I don't want to step on your toes, but I mean, I have a really interesting question. Actually, at the beginning of the presentation, you said that the goal was to reach 90% or something like that of efficiency. So, I mean, and it looks like that, okay, if I want to increase the efficiency, I mean, regarding the inductor design, I have to increase the switching frequency. However,
Yes.
I mean, the silicon limits are quite obvious. So, I mean, in your opinion, what would be the, let's say, what should be the approach to increase the efficiency right now with the current technology? If you can answer in 1 minute.
If I can answer that question in 1 minute, I don't think that there is a room to improve the efficiency, because you can have a car that has a really good engine and really good tires, but
the driver is low.
Yes, no, the car can go, I don't know how many rotations. The engine can give it how many rotations, and the tire can support I don't know what, but together they cannot go as fast as you want it, because you have these limitations on one and the other. So I don't know, with the current technology that we are using, we cannot achieve the high efficiency that we expect.
So, for example, in the case of silicon, I mean, should we go to the, let's say, smaller technology, or should we change the technology, like to go to the gallium nitride or something like that?
For these low voltage applications, so far GaN doesn't have any room there. Mm-hmm. But of course, in the future, I think that it's going to be really, really interesting to work with that. The issue here is this is automotive approved technology, so you cannot just change it like you want it. You need to have a certificate that it will work with in all that conditions. And at the moment, I only see that somehow to improve the existing technology. I don't know really how, since I'm not on the physics, I'm more on the applications.
We have time for one quick question, if any. If not, let's thank once again to Vladimir for this presentation.